I'm on. All right. Here's a question for you. Ready? The marker failed. There's a character from a strange language that I'm assuming you don't speak or read. But my question to you is, what does that mean? What does it mean? Again, I wish you were all here in the class because I'd be looking at you and you'd be looking at me and I would say, come on, what does it mean? Figure it out. Figure it out. Figure it out. And maybe I'd wait a minute or so and nobody would figure it out. And what we would realize is that's a ridiculous thing for me to task you to do. You can't figure it out. You either know what it means or you don't. And if you don't, you'd have to look it up. Now, let's suppose you look this up and this meant house. What if someone asked you, how did this squiggly line become that E? Your response should be, well, the squiggly line didn't become that E. It's just this is what we use to represent a concept or an object in one language, and this is how we represent it in another language. And the only way that you can know that this equals this, the only way, is if you know, or you look it up. It's a definition. It's declared. So you can't figure it out. Now, what I'm going to write down right now, well, hey, let me show you a mathematical example that I have showed you before in a previous video. But suppose someone did not know what that meant. They didn't know what division meant. What you could say is this, hey, let me replace this with means. And again, there are fancier ways in mathematics to say this, the famous if and only if, but or it's equivalent to, but it means it's good enough for our purposes here. So this means B times C equals A. Now, what have I done here? I've taken a more advanced, difficult, complex. I've taken a new concept and I've defined it in terms of something you already know. Hey, that's what we do with words. Usually I would say somebody pick a letter and I would try to pick a word that probably, I don't know, maybe most people don't know. Say, I don't know, avarice, it means greed. Maybe not exactly so in terms of language. It's debatable if we have exact synonyms, but nonetheless, this does mean this. Hey, how about this? If someone didn't know what the square root of A, say the square root of A equals B, what does that even mean? I suppose you'd never heard of square root before and you didn't know what it meant. Well, it's my obligation, or whoever is showing you this, they're obligated to tell you what it means, and what it means is B squared equals A. Well, I want to do this for a logarithm. And the most important thing about a logarithm is that you know its definition. If you don't know the definition of a logarithm, there's no hope. There's no hope. It would be like me asking you to tell me about this if you didn't know what it meant. There's just no hope. And this, I find, is the biggest issue when it comes to logarithms. And I'll get to the second issue in a minute. Because believe me, as soon as I show you the definition, you should have another question almost immediately. You really should. But let me just show you the definition of a logarithm. So this is a definition. You don't figure this out. You have to know it. And I'll be honest, you really should know it. And I mean, memorize it. Whatever word you want to use. But here we go. The logarithm of, let's say, x with base b. Now, there is some terminology, and you do want to know this terminology. LOG stands for logarithm. Somebody asked me recently if I could write that out, and I hesitated for a second, and I thought, wow, I don't know that I'd ever written the entire word out. I've said the word logarithm tens of thousands of times, but I'm not sure I've ever written it out. I'm not going to now. So everyone writes it like this. And if you look at any calculator, that's the way you'll see it, LG. This number down here, remember, if you're seeing this for the first time, I know that this doesn't make any sense. I know. This can't, well, I don't mean it doesn't make any sense, but what I'm writing now has no meaning. I'm going to give it meaning in a second. But this symbol or number, the subscript down here is called the base of the logarithm. So I used a B, although you could use any letter. X is just, it just represents some number. And then over here equals Y. Now, what you're looking at right here, I'm going to assume you probably have seen before, but I kind of wish you hadn't. Because if you had never seen this, then I would know that you cannot know what that means. And now it's my job, my responsibility, my obligation to tell you what it means. So what this means here, this means, and let me write this down and I'll get out of the way. Now, this is the definition of a logarithm. Now, here's a couple of follow-on questions. If you're seeing this for the first time, probably you look at this and your eyes glaze over and it's just, I don't know, it doesn't mean anything. That would be a very normal, natural, actually appropriate response. I mean, I know it may sound funny, but I think a bit of confusion when you first look at this as to what are we doing? What is that? That is to be expected. The second follow-on question is, why would anyone do this? As a matter of fact, if this means this, why not just stick with this? Because we're much more familiar and maybe much more comfortable with exponents. So if we're much more familiar, much more comfortable with exponents, why do this? The why we're going to do this, you are going to see as we go along. You're going to see. The confusion about the whole thing, that will leave you, that confusion. Maybe sooner, maybe later, it depends with practice. But the first thing is you should memorize this. Now, if you refuse to memorize it or you just really hate memorizing, here's what I'd like you to do for the sake of your sanity. When you're studying the textbook, when you're doing problems that involve a logarithm, keep this written down nearby so it's within view. I don't mean buried away somewhere in your notes. I mean it should be right in front of you. That will be one of the most helpful things that you can do. Is literally have this, I don't know, next to the book, next to your computer screen, paste it on the wall. Have this so that you can see it. And I'm going to refer to it many, many, many times. Now, I'm going to go ahead and do a couple of very basic logarithm problems. Again, in the back of your mind, you might be thinking, okay, I see what you're doing and I could do that, but I kind of don't know why we're doing it. And again, that's really, you should be thinking that for now, but you'll see why. Not in this video, but you'll see why. So I'm going to read this the way that these things are read. I'm going to speak. I'm going to say, I'm going to talk. I can't think of the right words here. I'm going to talk in a way which aligns itself completely with the way people talk about these things. Do you have to speak this? No. I'm not going to hear you ever speak this unless, if you're part of a Zoom call, then actually I will. But if you're just doing your exams, I'll never know. But this is read logarithm. And I would read this, the logarithm of 8 with base 2. So again, I would read this. This is the log or the logarithm, the log of 8 with base 2. Now, here's how I think about it. I'm a little hesitant to say this because, in a way, as a mathematician, maybe I shouldn't admit to this. But I like the idea, the analogy of a language you're learning. Suppose you've decided to learn Swahili or Arabic, or pick a language, make up a language. When you're first learning the language, almost certainly what you're doing is when you hear the language, you're translating to a language that you feel more comfortable with. I don't know that that's an absolute property of the universe, but at first you hear this new language and your brain doesn't know what it means. Your brain thinks, what? And then you translate. Like that funny character I made up, and then you say, oh, yeah, it means house. And then you go on about your business. If you're doing logarithms for the first time or you haven't done a lot of logarithms, almost certainly you're going to look at this and you're going to think, what? You won't know what it means. Now we're going to translate. We're going to translate from the language of logarithms to the language of exponents. So look at this pattern up here and use this. The b is 2, the x is 8, and the y is the question mark. So let's translate it. And translated, what this means is 2 to the equals 8. So 2 to the what power equals 8? Well, 2 times 2 is 4, times 2 is 8. The answer is 3. It is that easy. It is that easy. If you know the definition of a logarithm. If you don't know the definition of a logarithm, it's hopeless. So knowing this definition or having it ready at hand is critical and is indispensable. There's no way around it. There's no way around it. Here, let me try another one. And tell you, well, you want to memorize this ultimately. You really do. So let's say I said the logarithm of 81 with base 3. Now this may seem like a strange choice, particularly the 81. I am choosing these numbers right now, so these will come out nice. I am. And the obvious question is, what do you do when the numbers don't come out nice? Well, hold on to that question for a minute. So I look at this and I think, I don't know. Maybe you think, I don't speak the language of logarithms. This doesn't really mean anything to me. Translate. So we get 3 raised to the equals 81. Now, you probably don't walk around knowing 3 raised to what power equals 81, but here's where you want to realize something, that when I or the book asks you to do this, in particular asks you to do it without a calculator, we're choosing the number so this comes out nice. So let's give it a try here. 3 times 3 is 9, times 3 is 27, and you want to guess what 3 times 27 is? Yeah, 81. So this is 4. How about this? How about the logarithm where the base is pi of 1? Okay, now certainly now you must be thinking, hey, this has got to be a calculator problem, right? I mean, come on. Look at, once you're involving the number of pi's, the number of epsilon. No, wait a second. I don't know what this is. Let's translate. Pi to the equals 1. Well, this you should just know. You should just know. It's 0. Because anything raised to the power of 0 is 1. So this is 0. So this was actually the easiest one. There was nothing to calculate here. You didn't have to calculate a thing. But you had to know a fact. So there are these facts, that you just have to know, and there's no getting around it. And moving forward in math, this definition is one of those facts that you just have to know. Now, how do I think you get to know it? Here's how I think you get to know it. You take something like this, say the logarithm of 125 where the base is 5, and you work problems like this. Because every time you work a problem like this, you have to refer back to this original definition. So you think, I don't know what that is. Well, what does this mean? 5 to the equals 125. 5 times 5 is 25 times 5 is 125. So this is 3. How about this? How about the logarithm of 1 over 32 where the base is 2? Well, come on, that looks like you must have to use a calculator for that. Not so fast. So let's say question mark. It's the world's worst question mark. Question mark. So 2 raised to the what power equals 32? Well, not 32. That was wishful thinking, huh? 1 over 32. Well, when I wrote down 32 is because I was thinking 2 times 2 is 4, 8, 16, 32. but it's not 32. It's 1 over 32. So how do we achieve that? Well, this is based on your, having done practice problems the next month is. So -5. So this is -5, right? Because 2 to the -5 is 1 over 2 to the 5th, which is 1 over 32. This is a definition of logarithms. I can't, this is one of those things, it's like doing fractions or being able to work with becoming skilled with working with fractions. This is something I cannot overemphasize how important it is to know that this exists and then to know it. Now I want to do one more problem and then we'll call it for this video. Consider the following. You know how to solve that. And you know how to solve it by inspection, just by looking at it, right? But if you didn't, let's put the number 5 in here. We've done this. We have a way of solving this. We square root both sides, and we get x equals the square root of 5. Because we know, because I talked about it at length in some previous video, that the square root of anything squared is the thing itself. The square roots and squares are inverse functions to each other. They undo each other. If you square something, square root, you're right back to where you started from. Or if you square root and square, you're right back to where you started from. But what if we have this? Well, this you can do by inspection. You just look at it. You just look at it and you know. So I'll give you, here, let me erase this. You just look at that and you think, okay, 2, 4, 8, 16. Okay, fine, 4. But what if I do that? Well, 2 times 2 is 4. 2 times 2 is 8. Oops, I went too far. Now, you might start to detect a certain pattern here in mathematics, and that's when things are not nice. They're really not nice. And what I mean by that is, I'm not going to prove this right now because it's not a particularly easy way to prove it, but when it comes to logarithms, really, if it isn't nice, the answer is an irrational number. So what that means is you're not going to get this by guessing. You're not going to get it by guessing. So what are we going to do? How are we going to handle this? If you take a square root on both sides, that does nothing. Well, here's what we're going to do. We're going to translate this back into logarithms. And so if I go back this direction here, like this, and I always find this direction takes a little, I don't know, some extra level of thought. But look, the 2 is the b, so here, logarithm. What's the b? That's 2. Now, what's the x? Well, the x is the x, so that, wait a minute, hold on a second. Maybe I should have used, it just came over my computer. So maybe I should have used a different letter. What I did is not wrong. You might say it's awkward. But look, the way this is right here, the 5 is the x. Now, I can change symbols here. So as a matter of fact, I don't know if I should change symbols or not. I don't know what the best approach is. Let me leave it like this. In this problem right here, the 5 is in the position of the x, so we put the 5 here. Now, in a way, you could say what's left over. What's left over is the x. Let me rewrite this like this. X equals the logarithm of 5 and base 2. That's the answer. Now, I feel like most people say, yeah, but what does that equal? That's the answer. And you will say, yeah, but what does it equal? Remember, like with square roots? I talked about this at length. No, that's really, really the answer. Like, really, really the answer. But let's suppose you say, well, I cannot tolerate this, or I cannot, for some reason, I find this unacceptable. Or maybe you're an engineer and you're doing an applied problem. We're going to see lots of applied problems. This is a section where we're going to focus a lot in the next couple of days on, for lack of a better term, word problems or application problems. They're really good. They're fairly realistic for this level of mathematics. They really are. And they're interesting too. So let's say that this answer right here is not good enough. Maybe I need to adjust a dial, a gauge, some measuring device, and that measuring device is not going to have the logarithm of 5 to the base 2 on it. Here's one approach we have, and yes, we are going to use this approach. We're going to use a calculator. And here we get into some difficulty in terms of what calculator do you have. Ultimately, I don't care. And I'll talk about it next video, how you calculate this with a calculator. There's a lot of different ways. You could use PhotoMath and just take a picture of it. Most modern calculators, they have a button that looks, and again, depending on the brand, the button may look a little bit different, but several calculators have a button that looks like this. And when you press the button, the cursor will flash here, and I would type in 2, and then usually you press equals, because it doesn't know, maybe you're going to press in 21 or 213, and then the cursor will flash here, and you would press in a 5 and equals, and it will give you the approximation. Now, the approximation here certainly is going to be 2 point something. I don't know what. I could guess it would probably be 2.2 or 2.3 if I had to guess, but hey, how do I know it's 2 point something? Because again, 2 times 2 is 4, not enough. 2 times 3 is 8, too much. So it's between 2 and 3. That we know just by looking at it. Okay. The next question is, well, how did the calculator do this? We're not going to answer that at all in this class. If you make it to Calculus 2 in your life, and you never know, you certainly might, you will find out. It's one of the things that I love to do, is you can finally show everybody how your calculator does all these magical things. And yes, it does involve calculus. But for right now, as far as we know, the calculator is an oracle. Is just a magical device, and it somehow computes this. Okay. Let me do one more problem like this. Like, what do I mean like this? Well, here, let me erase this. If I write this down, say the logarithm of 7 where the base is 3. Now, what does this equal? Strictly speaking, this is called a logarithmic equation. It's an equation. There's an unknown. Now here, I've got the unknown isolated. Okay, fine. Nonetheless, it's a logarithmic equation. And what is the answer? Well, you're looking at it. So it would be a little bit like if I said, hey, x equals 2. Yeah, that's an equation, but what's the answer? X equals 2. Now, on the other hand, I could have written down this. 3 raised to the power of x equals 7. This is an exponential equation. The unknown is up in an exponent. And what's the solution for this? This. In fact, how did I go from here to here? We use this definition. We use this definition. This is one language. This is another language. I translate it from one language to the other. The only way to do that is to know this, so you've got to know this. So if I haven't said this enough times already, the real point really of the last 23 minutes here is you have to know this. If you don't have it memorized, write it on a piece of paper and have it next to you whenever you're doing anything with logarithms. Almost everything in Chapter 10, you're going to want to have this nearby. It doesn't mean you're going to use it in every single problem, but I would say over half the problems in Chapter 10, you're going to be using this. Okay. Now, we'll do graphing of logarithms, and we'll start doing applied problems in the next lecture. All right.